The topic is advances in petrochemical refining for improving efficiencies. So let me start with the fact that to understand the latest technology advancements in petrochemical refining for improving energy efficiency and how can the utilization of renewable sources or alternative feedstocks contribute to improving efficiencies. So we start with Pramod ji, followed by Dr. Pravesh, and then with Gaurang ji. So Pramod ji, your views on the latest technology advancements in petrochemical refining for improving energy efficiency, and how can the utilization of renewable sources or alternative feedstocks contribute to improving efficiencies.
Yeah, thank you, Prashant ji, and good morning to all. Basically, my background is with respect to R&D, so I'll put R&D perspectives also into the energy efficiency and the renewables. So typically, if we see these petrochemicals, the main feedstock is the cracker, right? And so far that well-proven or well-adopted technology is the naphtha cracker, which is a thermal cracking process. So typically the temperature, if you see, it hovers around 850 degrees centigrade to crack the naphtha. So there are certain technologies which, if it can be adopted, like the catalytic cracking of naphtha, so the temperature can be brought down from 850 to 600, 650 degrees centigrade. So that's one technology probably when we are going for any new technology for the cracker that can be adopted, and it has a lot of advantages. So that's one energy saving is very, very much seen into that. There are only 3 or 4 units running on those technologies. Ulsan and Malaysia, there are a couple of technologies. At HPCL also, we have developed the technology naphtha to olefins, which runs around 650 degrees centigrade. So that's a tremendous saving in that technologies. And now in terms of the other technological advancements, we are all talking about net zeros. So cracker is one of the technology wherein a lot of CO2 is emitted. So now a lot of people are talking about the electric furnaces. So all the licensors are looking into this, and there are a lot of solutions. Even demonstrations are also going from the different licensors. So probably that's the one when we can change into like CO2 emission will be almost nil if you go for the electric furnace. Then there are certain developments which is happening in the refining sites. One of them is for distillations, we use multiple distillation units. So there is a concept called divided wall column. So wherein like multiple columns can be merged into 1 or 2 divided wall columns, and that can improve the separation efficiencies. Because typically if we see in the petrochemicals, we are trying to separate the molecules. So if you can look into the divided wall columns, that has an energy saving, plot space saving, a lot of advantages into that. Then also we can look into other ways of separation. Typically we use distillation, and if you see in the petrochemical sites, to separate, let us say, propane from propylene, we have such a big columns lying in the refinery complex. So there are many developments happening in the area of membranes. Though only few demonstrations are there, but there are a lot of potentials into that. So a membrane can also be looked into for the separation of the molecules, because there we are looking into the pure molecules. Then we have a lot of energy guzzlers into the petrochemical complexes, and lot of few low value energies are there. So concept like organic Rankine cycles can be looked into, tap the lowest energy which can be used into the different applications. So these are the few things which can be looked into to improve the efficiencies in the petrochemical sites. Now we are all talking about the net zeros, CO2 emissions reductions. So there are various ways which can be looked into. One of the prominent is putting the bio-based materials into the crackers. Like biofuel, bio-oil can be put into the crackers. But these bio-oil comes with its own challenges. Like oxygenates could be higher. Then there could be some metals and the silica contents. Those needs to be pre-treated prior to putting into the crackers. Then we are all talking about the circular economy. So if we see the plastics, like the polymers, if there are certain waste polymers that can be depolymerized, and those plastics oils can be processed into the crackers. And of course that contaminants and everything has to be taken care. So we have looked into that studies, and we have seen like certain percentage, like 5 to 6% of the bio oil and the plastic oils can be put into the crackers, and we can get into that net circularity of the products. And there are a lot of cost advantage of the circular polymers in the markets. So that's again a business case coming up into that area. Then one of the nuisance we are seeing with respect to the tire, and if you see, there is not a well-proven kind of environment in our system. Like plastics, if you see, people are just burning somewhere and they make the oil through the tire pyrolysis, and that is sold into that, not in a common market. So there is a potential to use that tire pyrolysis oil also into the crackers. So those kind of studies and the scopes we have seen, so that can reduce that CO2 emission from the petrochemical industry, and as well as also bring into circularity into the markets. So these are my views into the subject. Thank you.
With a promising growth rate of 1.3 to 1.5% of GDP growth rate, and it is expected to reach around $340 billion by 2040, right? So if you talk about the energy consumption of chemical and petrochemical sector, it consumes about 30% of entire industrial sector energy. So that is a huge number. And if you look in the perspective of energy transition and net zero goals, so this is going to be a very challenging figure. So efficiency is very important because in the path of decarbonization, efficiency is like it is assumed, it is estimated that like 51%, around 50% carbon abatement will come from energy efficiency alone. So if you talk about petrochemical sectors, as he rightly mentioned, that process like crackers, like these are energy guzzlers, and they operate with huge temperature differences, where we have streams with as high temperature as 850 and as low as minus 160 when separation is required. So heat integration is one of the aspects that can be looked into, and that is being done also by the ways of pinch analysis and various heat integration techniques. And refinery petrochemical integration is also one of the aspects where we share streams for heat, and mass transfer streams are being shared. So that is also a very energy efficient process. And there are also a lot of technological development we have come across, because if talking about crackers, earlier we used to have tail end crackers, right? Now we have front end crackers, right? So front end hydrogenation crackers are also very efficient, because in the separation you need less amount to process, right? So that is the case. And second aspect of energy efficiency can be achieved by the electrification, right? So that is the learning that we have learned from the refinery benchmarking outcomes. So this is one of the recommendation that your steam network size should be reduced, right? In terms of Solomon benchmarking, like there's an energy intensity EI figure, right? So that says if you reduce 1% of steam network size, it is corresponding to 1 point improvement in EI value, right? So that is the impressive figure. So industries are taking their call, and they are going forward for more motorized driven motors, right? Rather relying on the steam driven turbines, right? That is one other aspect. And heating, for going for the electric heating is also that he also covered that. That is one of the aspects. Now coming to the second part of your question, that is related to feedstock. So that is a very important thing, because if you talk about energy efficiency, then the first main important thing is that the right molecule should be treated in the right manner, right? So if you are processing a molecule where it is not supposed to be processed, you are losing efficiency, right? So if we compare in terms of petrochemicals for the feedstock per se, it is mainly driven by the availability. If you talk about Asia and India, this is mostly reliant on the naphtha-based crackers, right? So if you talk about, if compare naphtha-based crackers with the gas-based crackers, so there's a huge amount of efficiency and margin difference as well, right? So there are things moving forward, And like we are having some technologies like PDH is there, right? So if you want propylene, so you need not to go for processing entire through the crackers, you have to go for a PDH operation. That is very innovative way, and there's a lot of capacity addition is coming up in China, and in India also there are two plants are under commissioning phase, will be delivering products by 2006, 2007 almost, right? So that is going to be game changer. And also there are some advancement in terms of catalyst, which improves the separation process, and a lot of things that earlier speaker has also covered. In the separation, there is also some improvement is coming. And so these are the things, and renewables can also be incorporated. So that is the way we can also decarbonize the sector as well. So all these keeping together, I think that is playing a major role in improving efficiency. Thank you.
What percentage of renewable are you presently adding? 10%, 20%, or it can be completely renewable?
Yeah, as of now, there is not, because they are, since our grid is already being green, right? It's going to green, and MNRE data is saying like it is around 190 gigawatt capacity is already available in terms of RE at present, right? So nowadays, whatever the newer plants are coming, so they are majorly relying on the motor-driven motors, like electric-driven motors, right? And they are drawing power from the grid only, right? So that is the way that is helping, I think, improving efficiency and reaching the net zero targets as well.
Dr. Pravesh Kumar, your views first.
Yeah, good morning to everyone. So, as you know, the major problems the refining industry is facing today is one is the decarbonization, and the second is the energy transition. So, when you look at the energy transition, the gasoline demand is going to peak somewhere around 2030, while the diesel demand is going to peak somewhere around 2040. So whatever the refineries are producing, it needs to be converted to the petrochemical, while the petrochemical demand is going to increase from around 27 MMT per annum to around 87 by 2040. So there is a lot of integration between the refinery and petrochemicals need to be done to improve the efficiency. First of all, the delayed coker unit in the refineries, which produce around 30% coke, need to be converted to the hydrogen addition technologies, like the evaluated vat and the slurry vat, which gives the liquids which can be converted to the petrochemicals. Then, and these petrochemicals, okay, the naphtha can be processed into the naphtha cracker, and the BGO, it can go to the FCC type of unit. However, we will further require the high severity FCC like the ENDMAX, which gives higher amount of olefins to the refineries or to the petrochemicals. Then this CO2 configuration is also coming up. In the COTC configuration in the future, we will not be required, okay, we will not be requiring the liquid fuels. So in the CO2 configuration, the crude oil can be directly converted to chemicals without the liquids. So a typical refinery as of now is having around 6 to 10% of petrochemical intensity index. It means it produces around 10% of the, but with the CO2 configuration, it can go up to 70% of the petrochemicals it can produce. Further, then coming to the renewables. So the refineries of the future will be producing the bio oil, the pyrolysis oil. Indian Oil R&D also developed a process, Indico P2F, in which the waste plastic can be directly processed to the coker unit and can be converted to the fuels. Then there is 2G ethanol plant at the Panipat refinery, where the ethanol, okay, where the rice straw or the paddy straw can be converted to the ethanol, and then it is being blended with the gasoline. The ethanol in the future, in case of surplus ethanol, this can also convert it to the ethylene as a green petrochemical. Then the 3G ethanol, in which the refinery of gases are being converted to the ethanol. So all these are helping refineries to convert, to meet their decarbonization target, the net zero target, as well as to handle the energy transition. Thank you.
Thank you, Dr. Parvez ji. Now we come to the use of digital in a petrochemical refinery, and what we are seeing is they are now going for, or they have really opted for AI and ML operations or algorithms, and they have also opted for digital twins. So my question to Partha Surji would be, how does these algorithms or data analytics or predictive maintenance helps in contributing or optimizing operational efficiencies and minimizing downtime in petrochemical refineries? So you handle both very in a seamless way. So you are the best person to answer this in the panel.
Very good morning to all of you. And today is a very everybody reached here with a lot of difficulties. There is a heavy downpour happening, so everything got delayed. So now we are trying to sling down. Soup more. So, ladies and gentlemen, it's my pleasure to be here. I have been coming in the NGN, maybe this is the fourth time, or so every time I come I always meet with new friends, new faces. It's my pleasure. And on behalf of Halida Petrochemicals, I'll be talking a little bit of my experience, what I have gathered over the years. Gentlemen, the petrochemicals and digitalizations, these two cannot be separated. They need to, like what he said, they need to get married together. So that is where I come from. The petrochemical manufacturing, it comprises many subsets, whether it is production, safety, the operations, maintenance. So when we really integrate every piece of these different segments of the entire slate of operation, even in our supply chain, so that gives you altogether different kind of ball game, where we keep on integrating one after the other. So there is a semblance. I put it like this. We talk about petrochemicals and chemicals. So the one thing we must understand, we come from, the particle. Then the particle goes into a different form, is a molecule. A molecule, nothing but, the different atom get together, turn into a, we have different kind of functional groups. So these functional groups, you don't know how they behave, like two humans sitting together side by side, the way we interact. These functional groups, they also talk to each other. They have a different, and every functional groups, every aspect of the interaction that takes place in the process of handling that we need to understand. And it is very, very complex, where the digitalization comes in. The larger part of it, I'll talk in different terms altogether, different way. But to put it in simple perspective, if I want to really understand and put every complex integration and the processes into one theme, that is a process safety management. So process safety management is a large part of the whole subsets that can be built into a digitalization. The process of digitalization you bring in and see the kind of value it delivers. When you talk about efficiencies, unless those parts are well taken care, the part of the operation will not come up the way we expect, the efficiency we cannot desire. So every minute downtime, every hours we lose in the process of this, so that gives you altogether different impact that nobody want to have. So digitalization is one thing I call it. It has three basic elements. It has the power of conceptualization, first. Second, it has the capacity to compare. And third, it is the collaboration. So these three things, if we keep in our mind, it goes and build on it, you can make a significant change. Possibly our human brain and our natural way of working, the brain keeps on moving one point to another every time, so you cannot bring it there. So there comes the question of digital twin. Digital twin, what he rightly, the question was, the AI ML, I call it the data that we bring in, real-time data, and structured or unstructured data. When you really bring it and mesh it together, we find and build on capabilities and capacities. And there are new things coming up. I'm a basically chemical engineer, but doesn't understand much about it. But I can say that the large language models, the AI, everything like, when you are coming, your flight is, 30 minutes delayed. So that kind of, information, if every person gets it on his mobile, there is a slippage, the bearing temperature has gone up, there is a, vibration has gone up, larger machines. So every component of the manufacturing systems, like a turbine, a motor, or a pumps, for a turbine or a compressor, you build on it and see what kind of, information you get it, and what kind of analytics you get it. We can prepare ourselves, and there are lot many engines can be built on it, and we get a different kind of inferences, and based on which these actual performance, say, I have designed an equipment for a particular efficiency and particular capability. So the history repeats, so the entire life cycle, or the point you have started gathering this data, you know where was my capability. One day I ran my maximum, so I finished the target, and I had the rate that I achieved. The same kind of capability, the information gives, the parameters tries to push on it. So then on this, you bring on the advanced process control, and you reach the desired destination every time. That is the target. That is the two parameters, the set point and the actual performance process value. How do you bridge these two? This kind of things, the digital twins and the advanced process control possibly reach there, and you can maximize the asset efficiency to give higher value from the same kind of people, same asset, same plant, and of course, at every time you are exceeding the target. That is where the AI ML and the digital twin can serve you better from the operations perspective of it.
Thank you, Partha ji. Now we come to the catalyst design part of it, and how it can be enhanced in the petrochemical refining processes. New technologies like COTC and naphtha to ethane process and its implication. So we start with Gaurang ji, and then Pramod ji, and then Dr. Pravesh.
Thank you, Prashant ji. Catalyst is a very important thing for petrochemicals, and it is ever evolving. A lot of things are happening. If you talk about FCC, there are a lot of improvement and improvement in designs have come up in the field of catalyst. We have improved a lot of propylene yield and LPG yield in terms of FCC. So a lot of things are happening in the catalyst in terms of separation also, and it is improving efficiency of the entire petrochemical sector, right? But there is another aspect of this thing as well, because if you talk about energy transition, a lot of things are happening, and the demand of petrochemical fuels are coming down. As it is expected that gasoline demand is expected to peak around 2035 around, LPG around 2032, and diesel around 2040. I'm talking about India. And it is happening much earlier in the Western countries as well, right? So what is the present data is saying? The data is saying that even FCC is not operating at a good margins at present now, right? So a lot of FCCs are operating at below capacity utilization also, right? So that is the figure. So looking at the picture as a whole, so there comes a need for some improvement and new technologies. Then we talk about like COTC and naphtha to propane and ethane technology, right? So I have earlier also mentioned, because if you talk about emissions and efficiency, then right molecules should be treated in the right manner, right? So considering the energy scenario and expectations, because I was going through one report of IEA about India. So that says because of electrification and electric vehicles penetration in the market, up to 2030, gasoline demand is very much moderated, right? So there's going to be a significant pool for available for petrochemicals in terms of naphtha, right? So, but and refineries is also like revisiting their capacities, because at present the capacities are around 253 MMT, and the announced plans are to reach up to 310 MMT capacity by 2030, right? And we are still working for what the capacity should be for beyond 2030, right? So looking at the picture, so it is very much understood that you are not going to set up a refinery for only the sake of the petrochemicals. Right? So there has to be something, new technology has to be there. Then the COTC is very promising, right? If you talk about COTC, some multi-zone cracking system is there, right? So there you need not to go for the entire producing the unnecessary fuels where demand is less. You directly produce whatever the petrochemical product is required. And COTC is promising the technology benefits of steam crackers, MTO, and FCC all together. Another aspect is very innovative innovation, and that is naphtha to ethane and naphtha to propane. I think recent white paper has been also in the market, right? So what that particular process says, here you just feedstock is naphtha and LPG. You process that, hydrotreat that naphtha, and finally then you get propylene and ethane. Propane and ethane. Then you have options like you can go for a gas cracker, ethane cracker, and PDH in combination, right? So here you are just treating the right molecule in the right manner, and you are improving efficiency as well. Because if we compare liquid feedstock based crackers with respect to gas-based crackers, so for example, if you have to set up 1.5 MMT of capacity of cracker, you require around 4.5 MMT of feedstock of naphtha, right? So in the terms of size, it is huge. It's consuming more energy as well. Capex is also more. So switching to the gas-based cracker is very important, right? But now we're talking about the ethane sourcing. All these things also is much talked about nowadays. But there are also some concerns. So if such technologies like naphtha hydrotreating and naphtha to ethane, naphtha to propane comes up, so that is going to be very beneficial and game changer in the future. Because if I talk about petrochemicals, like the methane is a molecule that you do not want to produce, right, in the petrochemical process, because here you are losing one carbon, and it's not about only one carbon. One carbon is taking away 4 hydrogen atoms as well, and hydrogen is very important commodity as of now, right? So in petrochemicals, the other aspect is that your carbon is being locked, right? So it is helping also. So if you are not emitting methane, you are just reducing by some optimization and some processes are coming. So that is also helping the entire sector. Thank you.
Yeah, thank you, Prashantji. Maybe I'll put this entire perspective in a little different way. If we see this oil and gas industry, first, the refining industry has come. There was hardly petrochemical intensity through FCC, maybe 2 to 3%. And in parallel, to meet the requirement of the petrochemical, standalone petrochemical complexes were put like Halida Petrochemicals, then IPCL. Then as the petrochemical demand increased, the refiners started integrating refining and petrochemicals like Indian Oil Panipat. Then HPCL is now setting up the HRRL. So if you see the integration from the crude, almost like HRRL, we have 28% of the petrochemical intensity. So that's probably up to 30% we can get the petrochemical from the crude. Now we are all talking about COTC. So if you understand a little bit about the COTC, what these licensors probably are trying to do is lot of integration between the existing technologies, like you have CDUs, VDUs, FCC, whatever the gases are coming. So those kind of integration along with the crackers. And almost like if we see in the China's, few units are running, which is integration of these available technologies, wherein around 40 to 45% of the crude can be converted into the petrochemicals. So COTC, what they say is anything more than 40% petrochemical intensity is called COTC. So this is the current existing technologies available, which is based on the integration. So now being an R&D, we looked into, is this the best way of producing the chemicals or there is something innovative ways? So we looked into at HPCL, and instead of putting, let us say from the crude, you have the seed use, feed use, FCC, delayed cokers, and the naphtha goes into the crackers to make the monomers. So instead of that, we looked into a single unit. Can we have a single unit? While in crude, we'll go to a particular unit, and can we make 50% of the petrochemicals? Is this a doable case? And we have seen, yes, it is a doable case. You take a single unit, put the crude into that, and in the lab and in our R&D, we have seen almost 50% of the petrochemicals you can produce. And we have completed the pilot, and right now we are putting up a demo plant at our Vishak refinery 80 KTA. That is under construction now. Maybe by Q1 26, we will be seeing that unit up and running. So that's a kind of game changer technology. It is possible from the crude to chemicals, you can make almost like 50%. So that's the innovation probably can be looked into to produce the chemicals from the crude. So instead of having such a big complexes, only we'll have one unit and then some treatment units. So that will reduce the capex. Even the CO2 emission per ton of the ethylene is significantly reduced by these technologies. Temperature requirement is extremely low, and it requires all the innovative way of the catalyst. So these are all incorporated into such technologies. Now coming to the other way of like your naphtha to ethane and the propane. So if we see the right now the naphtha cracker technologies, what we do is whatever the light naphthas are there, we desulfurize and put it into the cracker. But probably that's not the right way, what my colleague has also told. The crackers are meant mainly for the gaseous feedstock. Then only we can, get the more benefit from the crackers. So what the licensors are now trying to propose is, before the cracker, put a technology called naphtha to ethane and the propane and produce gases like ethane and the propane. And if the ethane goes to the cracker, definitely we'll get higher ethylene. And whatever the propanes are going, PDS can be put to get the higher amount of the propylene. So these are like the upstream. If we put this kind of naphtha to ethane and propane upstream of the crackers, we can also debottleneck the crackers. There is enough cushion available in the crackers. Now another perspective, if we see in the crackers, we also produce methane. Now what is the solution available for the methane? Almost if you see in the crackers, 15 to 16% is methane available. So what is the solution for that? So that also we have looked into. So if you put that naphtha to ethane upstream of this cracker, so you require hydrogen, right? So if the methane can be converted in the hydrogen, then can satisfy itself. So we looked into the solution, and we are right now into engineering of these solutions. So methane can be converted into the hydrogen that can go into that naphtha to ethane technology, and whatever carbon comes out of the methane, that's extremely premium carbon. And we call this as a carbon nanotube. The cost of carbon nanotube, depending on the quality, is extremely high. Almost like in a kg basis, if you see 3,000 to 4,000 rupees kg, it's extremely, extremely high. And there is no CO2 emission. When we convert this methane to hydrogen and carbon nanotube, if you put an electrical furnace for heating, for the temperature requirement, there is no CO2 emission. And we can valorize that carbon from the methane into a premium carbon. So these are the new technologies being looked into, which will definitely reduce the CO2 emission from the crackers and as well as valorize the molecules available into this. Thank you.
So, as we know, with the energy transition and the electric vehicle and the hydrogen vehicles are penetrating the vehicle market significantly, the fuel demand is going to go down. So what the refiners have to do with the existing asset where they are producing fuels. So these fuels or the crude oil need to be converted to the petrochemicals. So the existing units and the new units need to be integrated accordingly. So the hydrocracking unit type of unit which are currently producing the diesel, they need to produce naphtha which can be put into the naphtha cracker. So accordingly, the new catalyst need to be developed. The focus earlier, which was on the diesel, now moved to the naphtha. So the new catalyst need to be developed to produce more naphtha from the hydrocracker unit. Similarly, from the FCC unit, we need to develop the new catalyst where we can have higher petrochemical from the FCC units to be produced. Then the refineries of the future are going to be the biorefineries, or they are going to process the bio oil or the pyrolysis oil from the waste plastic. So this bio oil contains a lot amount of oxygen, so the deoxygenation catalyst need to be come up, new type of catalyst. And then for this pyrolysis oil also, we should be able to tune the properties, the quality of the product, whether we want aromatics or the olefins from the pyrolysis. So the new catalyst need to be developed accordingly. Okay, further, these bio oil or the pyrolysis oil, they contain a lot amount of metals and other impurities. So new dematerialization catalyst need to be developed for the hydrotreating or to utilize these into the refineries. Then coming to the COTC, actually COTC is nothing but a integrated configuration. You can have in a typical refinery, you produce fuel and then you convert it to the chemicals. However, for the CO2 configuration, you need not to go for the process of producing fuel, and you can directly produce chemicals by using a single R2 unit. But in the existing refinery, this naphtha cracker and the FCC are going to be an integral part of any refinery to produce the propylene and ethylene, because the propylene you get from the FCC, maximum propylene you get from the FCC, while for the ethylene you require the naphtha cracker. So ultimately, we feel that in India, not a single these refineries will be integrated and converted to the petrochemical refinery, rather than a single unit of COTC will come up, because it is a very expensive process. For a 10 MMTP of COTC configuration, you require around 60,000 to 70,000 crore. Indian R&D also developed different type of COTC configuration. However, these are so capex intensive that not a single configuration or the grassroots COTC we see in the near future. Thank you.
Thank you, sir. Now we come to the innovative solutions for reducing emissions. Is there a possibility, or because these are all fuel guzzlers, so how do we reduce emissions? To start with Partha ji, Gaurang ji, and Dr. Pravesh. Short answers, sir.
Yeah, definitely. Now, once again, the petrochemicals, once it is set, I'll put it simply, it is very, very difficult to really bring down the state where you are already there. But there are daily operations which goes as a right. There are 3-4 things we can possibly do on a operational perspective of any petrochemicals operations, like how do you manage the turnaround and how do you manage the the slowdown. If my turnaround planning is perfect, there are 2 OPEX part, I can bring it down, where the normal time, the slowdown kills me around 85% is the cost of energy. So if I do my turnaround properly and maintain it, I bring down the slowdown, means downtime of the plant, I can definitely bring down the specification, the consumption of the energy consumption to a large extent. That is one area. My yield goes up, my productivity goes up, I bring down the emissions. Second part of it, there are very ongoing, that will take much of time, but like if Mr. Gaurav has said, if I can bring down, my design theme should be such that I bring down my steam network. The compact the steam system, the better. Less and less amount of direct steam input into the everywhere. I don't want to put steam into the surface condensers where I lose lot of energy. I put into ultimately goes into the air. So I put lot of energy in, bring back the process streams, the cooling water systems as a whole. If my steam system, I can think logically and put more electrical systems into the operation, like electric furnace, which is a dream. Basically, there are few people are working, but still, even the lowest part of on the aux boilers or the HRSGs or in the steam cracker heaters, if I go for a combined, the power integrated, means I can produce power from there. So thereby, I can basically bring down my stack temperature and recover the energy from there. It's a combined turbine integrated, gas-fired integrated furnace where I can bring down the overall energy. So I bring down the, the overall CO2 footprint of the complex. That is one of the area we can definitely think of. And steam traps, insulation, etc. These are all very, very things. I am not going to elaborate much on this. Thank you.
Yeah. Looking at the emissions, I told earlier that this sector is consumes around 30% of energy of industrial sector. But in terms of CO2 emission, it is only 18%. That is because most of the carbon is being locked in petrochemicals, right, products. So now looking at where these emissions are coming from, in the particular process, one emission is occurring from the heat required, heating of emission occurred during heating, then due to feedstock consumption, then after waste. So if we take care of that heating is like converted into the electrical heating, that is the major aspect. Then if we can develop an ecosystem of recycling of products, that can take care of that thing. And as I talked about, because carbon is being fixed in petrochemicals, so there are a lot of, like, if you're talking about innovations, then I can see the future is very promising. As of now, it is not economical viable, but you can look into, because you can get carbon from whatever the CO2 is emitting from off gases, right? And you can get hydrogen from green hydrogen. You can produce petrochemicals. So that can be the future. That is very promising, and you have zero emissions. Instead, you are reducing CO2 emission, right? So that is the future. There are a lot of technologies are there of treating off gases, converting them to methanol, then methanol to olefin roots. You can produce petrochemicals. And also there are some efficiency and catalyst improvements are also there. We can improve the, like, whatever the carbon is being absorbed, and you can limit the carbon ejection, as the sir has told, because if you are limiting the methane formation, you are limiting the carbon being rejected. So these are the way. So I think the future is very promising, and that's all. Thank you.
Dr. Pravesh, your short answer.
Actually, refineries are doing many things to limit this carbon emission. Okay, consider the case of Indian Oil. Indian Oil emits around 24 million metric ton CO2 equivalent of GHG, scope 1 and scope 2 emission. However, with the current expansion, plant, it is going to go up to around 40 million metric ton CO2 equivalent. So to reduce this carbon emission, the different steps the refineries are taking, they are taking the renewable power from the grid, then energy efficiency improvement, then followed by the replacing of the steam heating with the electric heating, and then replacement of the liquid fuels with the natural gas or the compressed biogas. However, all these steps will reduce the carbon by around 25 million metric ton. So the remaining 15 million metric ton, we need to go for the CCUS, carbon capture and utilization, or for the carbon credit thing. So the Indian Oil is having the target of net zero by 2046, and we are hopeful that we will be able to achieve those targets by implementing all these steps.
Now we come to the last part, which is the CCUS. I don't know what portion of it are we capturing, and its implication in petrochemical refining. So short answers from Dr. Pravesh and then Mr. Pramod Kumar.
So CCUS is nothing but the carbon which we are emitting, we need to capture it, utilize it, or store it. So there are different technologies for the capturing of the carbon. India emits around 2.7 gigaton of CO2 equivalent. So, but there are some sectors like the petroleum where you can't avoid to emit the carbon. So you need to capture it. There are different technologies, the solvent-based, the adsorption-based, and then there is new, the direct air capture. However, the captured CO2, it need to be utilized. What we are going to the CO2 after we are capturing it. So it can be converted into the green urea, or it can be converted to the ethanol or methanol, or it can be converted to the syngas by getting the green hydrogen, and then CO2 can be converted to the CO, and then we can make the syngas, which can be converted to the fuels or chemicals. But not all the CO2 which we capture is going to be converted into the fuels. So the surplus CO2 need to be stored. It can be stored either into the oil wells for the enhanced oil recovery, or into the coal mines for the enhanced methane recovery, or in the saline aquifers. However, this CO2 capture CCUS process as of now is very expensive. So the government support will be required, and the policy support will be required to implement it at a bigger scale. Sorry. So because there will be separate entity for the capturing of the CO2, then to transport it to the utilization site or the storage sites. So with the government policy only, it can be implemented in a big way.
Sir, anything happening on the R&D part?
Actually, R&D, we have developed a process for the CO2 capture. So the typical absorption waste process gives around 90% efficiency, but with the enzymatic intervention, we have developed a process where we can get up to 95% CO2 capture efficiency. The process has been successfully demonstrated at a metric ton scale. However, we are looking what we are going to capture with this captured CO2.
Pramodji, your last views, and then we have a presentation. And then
Sure. So now if you, what my colleague told about that CO2 capture and utilization, the challenge is it with respect to the cost. So regeneration, as he told, so in HPCL also we looked into this. So typically if you see these absorption columns are very tall columns, right, almost 30-meter columns. So we developed a concept called HyG, means 30 meters columns can be brought down to a pump like 1.5 meter rotating device. So as Prashant ji told, we looked into this and we are setting up a demo plant in Vizag refinery, which is in advanced construction now. So that 30-meter column will come down to 1.5 meter column for CO2 capture. And this technology we tied up with KBR, which is licensing now globally worldwide. So now in terms of this CO2 capture, the other things other than this capturing is the utilization. So right now if we see there is a mammoth requirement to utilize this, but we are not finding in a larger scale. So definitely the support from the different forums is required to sustain this. Now in terms of the R&D, there are possibilities, technical possibilities to convert CO2 to methanol, ethanol, and even higher alcohols. People are also working into CO2 conversion to jet fuel. So that's also in advanced stage of this. And very innovatively, I have just seen few literatures and some labs are converting CO2 to carbon nanotube. So that can make this technology down the line sustainable. So of course, CO2 is not a waste, it's a molecule. How we can valorize and reap its benefits, R&D can support and make it successful.
Thank you, Pramodji.